Good morning, ladies and gentlemen. I'm Zhang, a junior student from Beihang University, China. It's my pleasure to introduce my work at the lecture session. The title of my report is Piezoelectric and Machine Learning-based Technique for Classifying Force Levels and Locations of Multiple Force Touch Events. My report is organized in 5 parts, including background, innovation, experiment protocol, methodology, results, and discussion. Human-machine interaction has roughly experienced these 4 stages of development. It is a process from professional to universal. Touch panel enables more people to use computers. It gradually becomes the most easily human-machine interaction in many fields, such as household appliance, public information, electronic games, industrial equipment, and so on. It has become the most easily accepted computer input mode after keyboard, mouse, writing pad, and voice input. This technology greatly facilitates users and becomes an attractive new multimedia interactive device. Take mobile phones as an example and review the evolution of the way which users interact with their devices. Initially, the user could only operate the phone by pressing several buttons in fixed position, which can be called one-dimensional manipulation. After Apple introduced the touchscreen and the gesture operation, users can move freely in the two-dimensional space of the touchscreen of the phone. So, it can be called two-dimensional operation mode. It is natural to wonder, if humans live in the three-dimensional space, why should the user's interaction with device only be in two-dimensional space? Is it possible to have three-dimensional interaction? So, what's the next step in touchscreen development? Force touch panels are welcomed in commercial interactive electronic products. For example, interactive display. Due to their ability to provide high human-machine interactive efficiency, current products such as iPhone X, Huawei Mate S, and ZTE AXON Mini can support single force touch event detection and classify the force amplitudes into 2 or 3 discrete levels. Nevertheless, in many application scenarios, multiple force touch events are required to be detected simultaneously with a high force resolution. For example, in a playing piano application, multiple keys may be stroked at the same time, and the sound amplitude is expected to have good resolution. Nevertheless, no solution is found in the literature now. To satisfy this urgent need, Hydroelectric touch panel in our previous work is used for detecting force touch events. The piezoelectric touch panel is made up of 4 layers: glass substrate, patent top ITO electrodes, PVDF force sensing layer, ITO ground electrode. The sensing ITO is etched as a 4x4 matrix, which contains 16 square-shaped elements. An optical clear adhesive is used to laminate layers. The choice of employing the piezoelectric touch panel is due to its high force detection sensitivity compared to piezoresistive and capacitive-based architecture. However, products using piezoelectric materials have faulty detection accuracy because of the unstable force-voltage responsibility and unavoidable interference. And what it specifically refers to is the propagated stress resulting from adjacent force touch. The issues above will become more complicated when two force touch events occur simultaneously. To sum up, it is difficult to establish a physical model and apply formulas to solve the problems. So, in this article, 3 typical machine learning algorithms are used to interpret the touch location and the force levels. The whole data acquisition and processing procedure are shown in the figure. When fingers touch the piezoelectric panel, the charge generated by the PVDF membrane is amplified by the charge amplifier and becomes a voltage signal. Then, the signal is sent to the MCU after a 16-bit ADC. Finally, the digital signal is transmitted to a PC to do data pre-processing and classification. According to our research, most people can easily distinguish 3 force levels, which are light, middle, and strong. Therefore, we designed the experimental protocol as follows. First, we perform the fundamental single-touch force detection by the piezoelectric panel. In the experiment, 3 volunteers were invited to touch the 16 locations, labeled from 1 to D, of the panel at 3 different force levels according to their personal feeling and experience. Second, they were asked to carry out multiple touch events by using 2 fingers simultaneously. We found that it is hard to precisely control the strength of 2 fingers at the same time. Hence, we consider 3 cases: light, middle, and strong. The pre-processing of data is conducted in MATLAB, and the specific steps are as follows. First, the DC offset is removed by subtracting the mean voltage of each channel. Second, envelope detection is conducted by the Hilbert transform method. Third, a trap filter is designed to eliminate power frequency interference of 50 Hz. Finally, the MATLAB function findPeaks was used to detect the peaks. A peaks of 16 channels may not appear at the same time. However, it is feasible to choose the time corresponding to the channel with largest value at the reference time. Then we assume the peaks of different channels were extracted based on the reference time. After the voltage peaks of each channel have been acquired, 3 typical machine learning algorithms are employed to classify locations and force levels. They are LightGBM, SVM, and ANN. The 3 machine learning methods are selected due to their superior performance in classification of complex signal. Table 1 and Table 2 respectively show the single-touch and double-touch test simplest performance on each model. Comparing the three classifiers, we find that AN performs better than its counterparts in both double-touch and single-touch detection. The detection accuracy of single-touch force level and location is 99.1% and 98%. Double-touch force level detection accuracy reaches 88.2%. Location detection accuracy reaches 92.3%. Our experimental results give the following facts. First, when the same classifier is extended from single-touch to multi-touch detection, the detection accuracy will decrease slightly. Second, the best algorithm for different users is distinct. Third, double force touch with 3 different force levels can be successfully obtained by the present research. Multi-touch event force levels and locations are successfully obtained by using a piezoelectric touch panel and machine learning algorithm. The work presented here showcases the ability to obtain force levels of multi-touch for the first time. The developed technique potentially enables more advanced and novel applications for users. Thank you for listening.